Recorded is rolling. It is Tuesday, May 13th. So we're going to knock out these quadrants in the quantum journal today. Also, some notes from above on, okay. Today is senior exams for science. Right? So anybody who's a senior, giving final exams for science today. Okay? And then all this week are senior exams. So got some other ones. Of course, everybody else, your exams aren't for a couple weeks. Okay? Laptops. So since we're winding down the year, you guys got to be turning your laptops. So seniors have to turn their laptops by this Friday. So you guys got 3 days. And then underclassmen, so everybody else, you guys got a couple weeks. Right? So Wednesday, the 28th is your last day of school. So just have it turned in by then. Now, the procedure for turning in laptops is you can turn your laptop to any teacher. Like I have a scanner up here. So, okay, walked in some wires there, but if you bring your laptop to me, I can open up a program, I can scan it with that scanner, scan the barcode, and that will check it back in the system. Also, make sure you also turn in your charger. I think on my end, I can check a box, just say that you also turn in the charger. And you guys see that Rolly card over there by the wall. So I'll just file away those laptops one by one in there. All right, so that's what I'll be doing. Okay. All right, and then another note, since we're on week 2 of AP exams, some issues they're running into is a lot of the AP exams are at least partially digital, if not fully digital. And so there's a program called Blue Book, and a lot of students are opening up Blue Book, but they haven't opened it in, say, a few weeks, so it needs to update, and it takes like a few minutes to update, and that's been holding back everybody's exam. So make sure if you have an upcoming AP exam this week, make sure you've opened Blue Book. Really recently, let's say in the last couple of days, so it's gone through all its updates. And another issue showed up is some students maybe don't know their email or password information. And now I don't know exactly what it looks like on your end, but something to do with it's not pre-stored. So students have to type it in and don't know the password, and that's caused a bunch of hangups. And so, of course, make sure you can log in with all that. Make sure all that login works before you go to an AP exam. All right. All right. So you guys good with the setup, what we're doing, agenda, I'll do. All right. All right. So let's look here. Last one we ended yesterday was Maxwell's Demon and land hour limit. That one was exciting. Right, there's this thermodynamic connection. There was this question of can you break the second law of thermodynamics with information? And the answer seems to be no, because it turns out that information is embedded in physical systems, and deletion of information requires energy. And you can show that the entropy increase by deleting that information would actually outweigh the increase in, the increase in entropy would outweigh the decrease by separating the hot from the cold. All right, so that's where we ended yesterday. And so let's look at superconductivity, which is going to lead into quantum locking, which has a pretty exciting video for you guys. So let's make a graph here for superconductivity. Show you guys this graph first, and then I'll show you guys my computer demo version of this here in a minute. So graph. Let's say you want to measure what's the resistance in a wire in ohms as a function of temperature in Kelvin. Or later, I'll pull up one that has resistivity in ohm meters. You guys remember a few weeks back calculating what is the resistivity of Play-Doh? I gave you guys some Play-Doh. You guys rolled it into a cylinder. You guys ran a current through that, measured the current. You guys measured what's the voltage, and were able to figure out the resistance. And then if you knew the cross-sectional area and the length of the Play-Doh cylinder, you could figure out the resistivity of that material. You guys remember that whole lab? Okay. Now, you guys were doing that all at room temperature, and the room temperature is, well, whatever it is in this room. So that was a constant. That was controlled. Okay. Now, over 100 years ago, public graph pretty soon shows going back to right after 1900, refrigeration had just come about. Said, hey, we can make these wires really, really, really cold. And actually, that turns out to be a variable also affecting the resistance from end to end, or the resistivity, if you like. Okay. Show hands. What do you guys think? What is this graph going to look like? So I'll narrow it down to 2 options. So let's start at room temperature. And then as you make it colder, 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 does a really, really cold wire have a lot of resistance or very little resistance? Right. So that's your 2 options. So if you start from room temperature and go colder, colder, how many of you guys think making the wire colder would have more resistance? Who says a colder wire has more resistance? Who thinks a colder wire has less resistance, less and less? Yeah, that's what it turned out to be. So maybe it started out like here. Right, so temperature in Kelvin, right, make it a little colder. It has actually less resistance. It's actually maybe more effective at transmitting a current. Now let's make it colder. Now it has even less resistance. And oh, look, all these dots. Look, they're lining up in like a straight line. Does that look pretty well linear? All right, so they kept going. They just make it colder, 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 colder. Okay. And then, completely unexpectedly, I don't think anybody was expecting this to happen at all. Suddenly, at some critical temperature, I'll label it T sub CR for critical, the resistance dropped all the way to zero. Or from a material point of view, you could say the resistivity of the material dropped all the way to zero. Ohms, or meters, right? So much like that. Right. And this part right here, that's called superconductive. Okay. Now superconductivity has some nice features, right? I mean, you can transmit a current with zero energy loss, right? Because there's zero resistance. Right? So one thing you might be able to do with this is, for example, run a current in a wire. So I'll have some current in amps here, and you can just have it loop in the wires round, sort of store energy, kind of like in a battery. Right? This next one we're going to be looking at quantum locking. You could get some really wacky looking levitation effects, right? Maybe you could create some crazy like flying car, maglev train kind of thing with this too, right? But the catch is that scientists have only found um, uh, materials to go superconductive at, well, it's not room temperature yet. So nobody's found a room temperature superconductive material yet. And so I'm gonna break out some demos for you guys. Let's start with this one. This is pretty much the graph that I just had you guys make. This was actual data. Now, I don't know what material this is, so that's lost from this graph. But some material. Now they put resistivity, so some material property, kind of like that Plato had some resistivity. Okay, so that's on the y-axis, and then x-axis you guys see is temperature in Kelvin. And you guys see where that critical temperature is. Now for this particular material, it looks like about 90 something Kelvin. So 90 something Kelvin. Keep in mind, in this room we're sitting in right now, isn't it pretty close to 300 Kelvin about? So let's call it about 300. Maybe it's like 290 something Kelvin. Okay, just round a little bit. Okay, so this is crazy, crazy cold. This is like colder than Antarctica cold, right, for this particular material. All right, what about other materials? Okay, so this one has some transparency thing. How to put some paint to make this work? So this is by year. So you guys see down here by year, going from 1900 to the 2010s, it looks like. Okay, so looks like, and then what was the critical temperature found to be for these different materials? So it looks like the first couple that were found of materials found to go superconductive are, guys, what is Hg? Is that mercury? And what is Pb? What is Pb? I think that's a good one to know. Hey, do you guys know plumbing? Plumbing. Yeah. So the old Latin term was pluvium because they used to create their water pipes out of what? We don't call it pluvium anymore. We call it what? Lead. That's lead. Okay. So mercury, lead can go superconductive, but guys, that's under 10 Kelvin. So that's getting really, really close to absolute zero. Now, it'd be nice to have something closer to room temperature that goes superconductive. So over the years, we got a collection up here. Okay, 150 Kelvin, that's still insanely cold, but right. And then this one at the top right, okay, 200 Kelvin, that's getting closer to room temperature. But there's a catch with this one, which is this is also at what 100 and something gigapascals. So okay, high pressures. Right, that could be variable too. Right. So what's something cool you can do with superconductive materials? All right, so let's look at quantum locking.
The phenomena we saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor. Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So electricity is the flow of electrons inside a material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation. It's quite remarkable. Think about it. In classical physics, there is always some friction, some energy loss, but not here, because it is a quantum effect. But that's not all, because superconductors don't like magnetic fields. So a superconductor will try to expel magnetic fields from the inside. And it has the means to do that by circulating currents. Now, the combination of both effects, the expulsion of magnetic field and zero electrical resistance, is exactly a superconductor. But the picture isn't always perfect, as we all know, and sometimes strands of magnetic field remain inside the superconductor. Now, under proper conditions, which we have here, these strands of magnetic field can be trapped inside the superconductor. And these strands of magnetic field inside the superconductor, they come in discrete quantities. Why? Because it is a quantum phenomenon, it's quantum physics. And it turns out that they behave like quantum particles. In this movie here, you can see how they flow one by one discretely. This is strands of magnetic field. These are not particles, but they behave like particles. So this is why we call this effect quantum levitation and quantum locking. But what happens to the superconductor when we put it inside a magnetic field? Well, first there are strands of magnetic field left inside, but now the superconductor doesn't like them moving around because their movement dissipate energy, which breaks the superconductivity state. So what it actually does, it locks these strands, which are called fluxons, and it locks these fluxons in place. And by doing that, what it actually does is locking itself in place. Why? Because any movement of the superconductor will change their place, will change their configuration. So we get quantum locking. And let me show you how this works. I have here a superconductor, which I wrapped up so it stays cold long enough. And when I place it on top of a regular magnet, it just stays locked in midair. Now, this is not just levitation, it's not just repulsion. I can rearrange the fluxons and it will be locked in this new configuration, like this, or move it slightly to the right or to the left. So this is quantum locking, actually locking, three-dimensional locking of the superconductor. Now, of course, I can turn it upside down and it will remain locked. Now that we understand that this levitation, so-called levitation, is actually locking, yeah, we understand that. You won't be surprised to hear that if I take this circular magnet, in which the magnetic field is the same all around, the superconductor will be able to freely rotate around the axis of the magnet. Why? Because as long as it rotates, the locking is maintained. You see, I can adjust and I can rotate the superconductor. We have frictionless motion. It is still levitating, but can move freely all around. So we have quantum locking and we can levitate it on top of this magnet. But how many fluxons, how many magnetic strands are there in a single disk like this? Well, we can calculate it, and it turns out quite a lot. 100 billion strands of magnetic field inside this 3-inch disc. But that's not the amazing part yet, because there is something I haven't told you yet. And and the amazing part is that this superconductor that you see here is only 0.5 micron thick. It's extremely thin. And this extremely thin layer is able to levitate more than 70,000 times its own weight. It's a remarkable effect. It's very strong. Now, I can extend this circular magnet and make whatever track I want. For example, I can make a large circular rail here. And when I place the superconducting disc on top of this rail, it moves freely. Again, that's not all. I can adjust its position like this and rotate, and it freely moves in this new position. And I can even try a new thing. Let's try it for the first time. I can take this disc and put it here. And while it stays here, don't move, I will try to rotate the track. And hopefully, if I did it correctly, it stays suspended.
So that's a pretty good showstopper shot right there. All right, so he has this superconductor. It's like a little hockey puck, like a little flying saucer. And he puts that in a magnetic field. And then, because we're talking about quantum mechanics, these magnetic field lines, well, they're kind of quantized, right? They act maybe like particles as much as like field lines or waves. We're going to call these fluxons. And the superconductor expels most of these fluxons, right? But maybe a few get trapped inside the superconductor. So it locks it in place relative to some magnetic field. Right? Then you saw the last few demos he was doing, saying, oh, hey, what if I have like a circular magnetic field or a track that goes in a circular shape? Right? You can get some kind of motion relative to that field that has some symmetry about it. Right? This next one I'm going to do a little backwards. So I'll give you guys the notes first, because all these demos I'm showing you, they're all paced differently, right? So some are a little longer. This next one's like a minute long, right? So what's another sort of engineering application of all this quantum mechanics is laser technology. How does the laser work? And so it's going to go like this. And I'll give you guys the notes first, then we'll look at the video. You got all this from, right? So what if you have a couple of mirrors and you bounce some light back and forth between these mirrors, right? Well, if you thought about this like in a classical situation and say, okay, well, it would just create light that bounced back and forth, and that would be all random, right? But in a quantum mechanics sense, these photons of light, like these particles of light, it's hard to distinguish these apart, right? So as they excite each other with energy, I'm going to say the photons are more likely, so like a statistical property, right? To be in phase and have the same polarization. Why? Because in quantum mechanics, particles, so like photons in this case, are not readily distinguishable. So what is one photon from another photon? If one photon is bouncing back and forth and exciting nearby photons, okay, it's not like a bunch of tennis balls bouncing around. There's ambiguity about where one photon ends, the next begins. Right? They're all sort of connected in a way. Okay? And then statistically, they're more likely to be all in phase. Okay? And that would be laser light. Right? So this makes a laser a laser. They're all same phase, same polarization.
To make a laser, all you need to do is give a big collection of atoms enough energy so they're excited and ready to emit light. Once one of them spontaneously emits a photon, it'll stimulate some of the others to do so, and you get a nice cascade of illumination. But instead of letting all the light escape, it's more powerful to trap it between two mirrors and let it bounce back and forth through the atoms. All that passing light will stimulate them to emit even more light, and as long as you keep on re-exciting the atoms, you're happy to go on emitting light forever. But why do the atoms emit light just because another photon passes by? It's actually pretty simple. Imagine flipping two coins. They can either be in the same state or in different states. But photons aren't like coins. No matter how hard you try, you can't tell one apart from another. So in a photon flipping experiment, that means there's only one way for them to be in different states, but two ways for them to be in the same state. So they're more likely to be in the same state. And in general, this implies that photons always want to be like other photons, to have the same phase, polarization, and go in the same direction. And what's more amazing is that if a solitary photon passes by an excited atom that could emit another photon, there's a good chance it will emit one, because the two photons want to be together, even before the second one exists. So once you have all these friendly photons bouncing around between the mirrors, you can just open up a little hole at the end and let out a blinding stream of coherent light. A laser beam.
All right, this next one, let's go to the edge of a black hole. So this is Hawking radiation.
Atoms are a bit like people. They're very hard to predict with absolute certainty. They do roughly what you would expect of them, but never exactly. With atoms, it's even hard to be totally certain whether they exist or not. Sometimes, Hawking knew, atoms pop up when there should be absolutely nothing around. In fact, out in space, it's happening all the time. The theory of the very tiny says space is never empty. At an atomic level, there is always a tiny, tiny amount of activity. But the theory of the very big says nothing exists at the edge of a black hole. Hawking realized this was where the two theories clashed. He had to find out what was really going on. According to the theory of the very tiny, in empty space, there are pairs of subatomic particles that emerge out of the void, exist for a tiny moment, and then destroy each other.
And so the idea is that out of nothing, if you like, a pair of particles is created and then exists for a short time and then annihilates. And that's happening throughout space. So it's happening there, and it's happening there, it's happening there.
This pair of particles is like yin and yang, night and day, opposites that would not exist without each other. One has positive mass and the other has negative mass. But Hawking asked, what would happen if this pair of particles bumped up against a black hole? Hawking realized that the positive particle would have just enough energy to escape the black hole, but the particle with negative mass would fall in. And it would do something extraordinary to the black hole.
Particle that goes inside the black hole eventually decreases the mass of the black hole. It effectively has negative mass, but the particle that goes off to the distant observer is there observed as part of radiation.
Although we now understand why black holes had to give off thermal radiation, that came as a complete surprise at the time. At first, I thought I must have made a mistake.
But Hawking had not made a mistake. Around a black hole is an almost imperceptible microscopic glow.
Dun, dun, dun. All right, so if you ask a question like, what's out in the middle of deep space, like out in the middle of nowhere? Right? Well, say if you get between Earth and Mars, maybe there's like a little bit of solar wind, or maybe like a few particles of hydrogen per cubic meter, right? What if you get out like between galaxies where there's like really empty, right? Might have just like one or two particles of hydrogen per cubic meter, or maybe not even that. Now that's from a classical point of view. But then if you talk to a quantum physicist, they'll say, well, there's actually these quantum fluctuations that are always happening on in the fabric of the universe. So you're always getting these particle-antiparticle pairs spontaneously created out of nothing. Right? And they have exact opposite properties. Right? So this is a completely random process. Right? The particle has positive mass and particle values, and the antiparticle has exactly opposite properties. So it'll have negative mass and negative energy. It'll have the opposite charge of the particle, like an electron versus a positron, have exactly opposite charge. Okay. Now, most of the time, most places in the universe, like even in this room, right, these quantum fluctuations could be happening. But most of the time, these two particles, the particle and the antiparticle, immediately annihilate each other, and it's like they never existed. Right. So conservation of energy holes, conservation of mass, right? It's all there. Right? It's like there's zero net effect, right? But around the periphery of a black hole, right, there's a certain boundary layer where you might have just the conditions where the particle that has positive energy might have enough energy to be able to escape the black hole, whereas the antiparticle with its negative mass would not, so that would fall into the black hole, right? So the antiparticle could fall in, but the particle might have enough energy to escape, right? There's some like boundary layer where that separation can happen, right? And the particle then goes on to the wider universe's Hawking radiation. That's what Hawking radiation is right there. So it's electromagnetic radiation. Okay? But the antiparticle that falls into the black hole, well, that's adding negative mass to the black hole. So you run this process long enough, and that will eventually cause the black hole to dissipate. Okay? Now, the amount of time that would take to happen is like an insane time scale. So to throw an order of magnitude on it, do you guys remember, or I'm sure this has come up at some point. Guys, how old is the universe? How many billions of years? Think about 13 to 14 billion, somewhere there, right? 13, 14 billion years, something like that, right? Which is, what is that as an order of magnitude? Like a billion is 10 to the 9, right? 10 to the 9. 10 billion would be 10 to the 10. So as an order of magnitude, our universe is a little over 10 to the 10 years old. So 10 to the power of 10. Between 10 and 10, 10 to the 11, right? So here, I Googled this question. How long would it take for a black hole to dissipate because this Hawking radiation, oh, there it is, Hawking radiation comes up. All I typed was how much time for black hole to dissipate, and Google gave me Hawking radiation, right, with their little AI program here. So a black hole with the mass of our sun, which by the way, our sun's not even big enough to turn into a black hole. You need usually start at least 3 times as big. But if there was one, take 10 to the 67 years. So the universe is only about 10 to the 10 years old, take 10 to the 67 to completely evaporate, right? Which is an insane time scale, right? Because like, how do you even like talk about that, right? And then say a supermassive black hole would be order of magnitude like, well, even longer than that, right? So some created, but time's ticking. So I guess there's a time out there where these things are going to evaporate. So I think you guys saw that in the astronomy videos we did back a little while too. So it's like the black hole era and like the dark era after that. Right. What else have we got on that one? Yeah. Okay. All right, let's do radiometric dating. All right, this could be carbon-14 dating or uranium-lead dating. All right, we'll be looking at. So I do want to do some calculations with you guys, but that's going to be mostly tomorrow's focus. Today, here, I want to do a graph with you guys and get the big idea of how this works and do a couple of examples. So a lot of particles, like most particles in this room, are stable, but there are some radioactive particles that want to decay to other things, and they'll have like some half-life, right? So if you look at the amount of substance you have as a function of time, or some concentration as a function of time, okay? Then you can start off with some initial amount. So at time 0, you'll have the initial amount, call it A naught, right? So that could be a point on this curve, right? But then different radioactive particles will have different associated half-lives. So after one half life, I'll call it T sub 1/2 for 1/2 life, you'll have half of the amount that you started with. So 1/2 A naught goes right here, point, okay? And then after another half life, so 2 T halves, right? You'll have, well, half of that half. So now you're down to a quarter of the original, right? And then after 3 half lives, you get half of that half, right? So now you're down to an eighth of the original amount, right? Now, mathematically, could this process go on forever, right? You could have like 10 half-lives, 12 half-lives, right? And you guys see this curve right here, right? This is called exponential decay. See how it asymptotically approaches zero, right? Asymptotically approaches zero, right? So you could wait like a billion years, and mathematically there might be like some number left over. Okay? Now, I wanted to describe this curve with two forms of equations that could both describe the exact same curve, right? And I'll just give you guys a couple of examples, right, to round out this quadrant. Right, so let's see if we can craft an equation for this. Like, what could this look like? So I can say the amount that I have after some time could be the initial amount times something, right? So I want to construct this with you guys so you guys can see why this equation would make sense, right? Right, so after 0 time, you should have the full amount. So now I haven't finished the equation yet, but time is going to be my sort of independent variable. Right? If I plug in 0 time, I should end up with the original A naught. Now the half-life is statistically the amount of time it would take for half to decay into whatever comes next. So I'll say times half, some number of times. Okay, some number of times. Okay. Here, just to give you a more concrete example. Here, let me write it down here. I'm going to come back and finish this. So carbon 14, right? Because most of the carbon in here right now, I mean, there's a lot of carbon in this. The vast majority of it is carbon 12, has 6 protons and 6 neutrons. But there's a couple of isotopes that are radioactive. One of them is carbon 14, and that has a half-life of 5,730 years. Okay. Now, there's not very much carbon 14 in all this. It's a tiny, tiny, tiny proportion. Okay. But however many atoms that you have, say if you had, just make up a number like 20 atoms of this, after you count 5,000 some years, now you're down to 10 atoms. And then after another 5,000 some years, now you're down to 5 atoms. And after another 5,000 some years, okay, it keeps going half and half and half, right? So I still need to finish this equation. So the amount that you end up with is the amount that you started with, that's A naught, times 1/2. Well, how many times is 1/2? Well, it depends how much time has passed. Don't you need to count a number of half-lives? Like, and wouldn't that show up as a power, right? As an exponent, right? So if exactly 1 half-life has passed, suppose it's been 5,700 years, so it's carbon 14, right? That would be multiplying by half one time, right? Does that make sense? Right? So here, guys, what's going to go in this exponent right here? How can you count the number of half-lives as a function of the total time that's passed? Here, guys, do this. It's T divided by T half, right? So it's all squeezed into that exponent right there. Right. So sorry, that kind of runs through that G right there on dating. Right. So the amount you have is the amount you started with times, and how many half-lives have passed, you want to multiply by half that many times. So it's times a half to the power of T over T half, where T half is particular to some substance. Like if I know I'm working with carbon 14, T half would be 5,730 years. And then, guys, if let's run a couple examples. Suppose 0 time has passed. Guys, what is 0 over 5,730? Would that be 0? Guys, what is 1/2 to the power of 0? 1. Aha, 1. And so if this is all 1, then A equals A naught, and that would be that point right there. You see where that point comes from? Right? Now, what if exactly 5,700 years have passed? What is 5,700 divided by 5,700? Would that be 1? Oh, and that's 1/2 to the power of 1, which is a half. That's to say you're multiplying by half 1 time. So now you have half of what you started with, which is that point right there. You see that? And then this process could just continue. You see that? Okay. Now, to tie this to an application, suppose you're an archaeologist one day and you find some old artifact, right? It's like buried way down, like 5 feet under the ground. You pull this up and it's some organic material, right? Maybe it's some cloth or some paper or like some bone or something that was alive at one point. Now, anything that's alive has a constant proportion of this carbon 14. Like all of us right now have a constant proportion some concentration of carbon-14 in this. Very, very, very tiny concentration. Okay. But as soon as living being dies, that organic material dies, then this will, the remaining carbon-14 will follow a curve that looks a lot like this one. Okay, it will tend towards zero. So suppose you find some artifact and you take it to the lab and it has, let's say, half of the carbon-14 that it should have had it been alive, right? Because if it has half the carbon-14, then how old is that artifact? About 5,700 years. You say, oh, this comes from probably about 2,000 or 3,000 BC, right? Because what if it has a quarter of the carbon-14 that it should have? A quarter of the carbon-14. How many half-lives is that? There's 2 half-lives, which would correspond to how many years? Maybe about 11,000, something like that. You say, oh, well, this artifact must be about 11,000 years old. You can keep going back. You can go back tens of thousands of years using this particular method. Okay? As long as it's organic material, right? And you can date it within probably about 50,000 years, so you could go back. Right? Like I said. Now, I told you guys I want to craft 2 equations with you guys. This is one equation. This is one form of this exponential decay. But there's another form. Here, maybe ask you guys. Oh, have you guys done exponential growth and decay in a math class? Because if you run into exponential growth and decay, there's a special base that mathematicians like to use. There's more like pure mathematical way to describe this equation or to describe this graph. Okay? And it doesn't use 1/2 as a base like I did in this this formula. Okay? Because what base is more like the mathematically pure base to describe exponential growth and decay? And it's a button on your calculator. Which key am I talking about? Oh, wait, what'd you say? E. Yeah, E. You guys see right here, there's a button that says LN. That stands for natural log, right? Natural log. And right above it in white, it says E to the power of. Do you guys see that? Okay. Here, guys, try this. I know everybody has one of these models within reach. Turn this on, hit second, and then hit that LN key, which really brings up E to the power of, right? And it should say E to the power of. Do you guys see that? You guys see E to the power of? Right? Type 1. We're just going to do E to the power of 1. And I bet most of you guys, actually all you guys should know this from a math class. There's a certain number of constants it's good to know before you get your high school diploma. Like if I said pi, you say, oh, 3.14, and it's irrational, so you got to cut off at some point. If I said phi, some of you guys might know phi is like 1.618. Golden ratio pops up a lot in nature, right? How about E? E to the power of 1. That's E, right? You guys know this one? What is this one? That's it. Yeah, 2.718, blah, 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 blah. Of course, it's also irrational, so, okay. So 2.718 something. Yeah, right. Now, what's special about this E, right? Which I still need to make an equation that involves that, but here, I'll give you guys a little bonus right here. Let's do a little bonus. This is outside of the journal. What's special about E? Right? So, say I made a graph. Let's do Y versus X. Let's say I want to graph Y equals E to the power of X. Just keep it real simple, real basic, right? Of course, you can expand that and do like continuous compounding interest rate or something, but all right, let's keep it real basic. Okay, guys, what's E to the power of 0? 1. So I know at 0, I have 1, so that's 0, 1. Point. That's the point of the graph right there. Okay, what's E to the power of 1? Aha, 2.718. So if I put a 1 here, 2, 3, call this about E. That's there, bam. It's that point right there. Okay. How about E squared? How about E to the power of 3? Does that take off real fast? Is that exponential growth? How about the other way? Guys, what's E to the negative 1? Is that 1 over E? And how about E to the negative 10? Is that 1 over E to the 10? Which approaches what value asymptotically? 0. Yeah, so I'm going to have this horizontal asymptote going off to the left. Okay, I want you guys to see how this logically goes together. It's going to create this exponential curve. So here's your basic exponential curve shape right here. Like I said, okay, so it asymptotically approaches 0 to the left, and it takes off real fast going to the right. Right. This is the power of interest rate. So if you have a little bit of spare cash lying around that you want to put into savings, especially if you're still in your 20s, see if you can put that in an index fund. It'll accumulate maybe like 5, 6, 7% continuously. By the time you're ready to retire, you got a lot of money. Okay. All right. Okay. So why E? What's special about this space? And I can show you at least one very interesting feature about this. Okay. Is because if you hold your ruler flush to the curve, wouldn't you be finding the slope? Okay. I'm tending towards a calculus concept here. Okay, how many guys are in calculus right now? Who's in calculus? All right, yeah, so I bet you know exactly where I'm going with this. Right? Because if I hold my ruler flush to the curve, let's put it right here. How about this? Right. And I find what's the rise over run. So take a triangle out of this. Say if you were trying to walk uphill, here I'll show a little guy trying to walk uphill. Isn't it getting steeper the more he's walking off to the right? Okay. And I'll call this slope dy over dx because I'm looking for maybe like delta y over delta x, but it's going to be an instantaneous rate of change at any one point. Is that okay? So I can make a second function. I can say, well, what are all these slopes? I see if as I go to the left, the slope is definitely going to approach 0, isn't it? As I go to the left, it approaches 0 slope. It's easy to walk on flat terrain. Okay? And then, it's getting really steep over here. So I'm going to call that curve dy over dx, just in general, dy over dx, which depends on what your x value is. So this is also going to be a function, right? And if you're in calculus, I bet you know the answer to this expression. What is the rate change of e to the x? Is it e to the x? It is. Guys, this is the only curve that does this. This is the only curve that the coordinate, like the y coordinate, is the slope. It's the same thing. So that's fun. Right? Is that fun? Yeah, you guys like that? All right. So, hey, how can we take this model and also describe this exact same curve? What if I don't want to base it by half? But let's do the more mathematically pure way to describe this. Okay, so let's start over. Let's do a equals a naught times. Okay, so it'll start out the same way. Okay, and then instead of a half, I'm going to put e. Right, so now I got this natural base. Right, this 2.718 irrational number. Okay. And I need a power. Now, guys, the fact that this curve is exponential decay for half-life, should the power be positive or negative? Yeah, it will be negative, right? Because it'd be like the opposite of this one. This one's growth, right? And then this one's decay. So let's do negative, and I'll do kt. I still need t as a variable, independent variable, right? But what is that k? Now that k is related to this half-life. If you know the half-life, you can do a little bit of math and solve for k. And that's one thing we're going to do tomorrow. So tomorrow, we're going to do some half-life calculations, right? Right. So we'll do an expanded version of this adventure tomorrow, right? All right. You guys good with that? All right, so I got some more stories with you guys with Half-Life. Where is this? All right, let's find a guy with a Geiger counter. You guys want to see a Geiger counter?
The normal background radiation sounds like this. But this rock a little more interesting.
Yeah, so he's seeing some radioactivity there. In fact, what I think he's looking at is right. It's probably a rock that had some uranium in it, right? All right, so here's the decay chain. There's uranium near the top. Now, above that is plutonium, but you guys probably remember from past few weeks that there's no natural plutonium in our environment, maybe in other solar systems, but whenever our solar system was created, it only went up to uranium, right? But uranium, well, 238 stable, but 235 is a particular isotope that is radioactive. And oh, guys, look at this red half-life right here, 0.71 gigayears. Is that like 700 million years? So a half-life of 700 million years. So half of this U-235 decays into thorium. That turns into, I think it's called palladium, I think. And then look, some of these half-lives are days. Some of these are like milliseconds. And then, oh, guys, look at the bottom of this decay chain. Guys, what is PB? Lead. Hey, we're back to lead. Now, lead is stable. So do you guys think if you found a very old rock and, well, actually, let's do the opposite. What if it was a freshly created rock, say out of a, I don't know, where is uranium created? Like either a supernova or colliding neutron stars or some version of that. Right? Wouldn't it be all uranium, like 100% uranium if it was brand new? But if this rock's been sitting around for a few billion years, I bet this proportion of lead is increasing. And if you know the proportion of lead to uranium, could you effectively date that rock, figure out how old that rock is? All right, you guys think? All right, so here, let's do a little story on a guy here. Right, his name is Claire Patterson. He realized that, and he was using this particular method to calculate what is the age of the Earth. Oh, I should ask you guys before I show you guys this page. Right? Does anybody know? I think this may have come up before in this class. Does anybody know how old is the Earth? How old is the Earth? how about let's see what he came up with. About 4.5 billion years, a figure that has been largely unchallenged since 1956. So back in 1956, he was using this method, looking at very old rocks, looking at proportions of different isotopes, different material. Right? Okay, 4.5 billion years, or you find rocks that old all around the Earth. So there was some event that happened 4.5 billion years ago, maybe some supernova or something, right? That created everything in our solar system. Okay. But this guy actually has another part to his story too, because do you guys think that in doing that calculation, he had to have a very clean environment that was not poisoned by lead? But this is back in the 1950s. So guess what was contaminating the environment all over the world in the 1950s? Lead. Do you guys know if you go to the gas station now, you buy unleaded gas? That's because of this guy right here. He goes, oh, hey, we're actually contaminating our entire environment with lead and like significantly reducing IQ points and all sorts of things. So yeah, that's a fun story too. That's a fun tie-in. But yeah, now we know the age of the Earth. Here, got one more on, but let's do the carbon version. Here's the carbon version.
Carbon is a critical ingredient for life on Earth. All living things are made up of about 25% carbon. The carbon atom is unique because it can bind to other carbon atoms to form long chains and rings. And these in turn serve as the backbone of complex molecules that make life possible. The nucleus of a typical carbon atom has 6 protons and 6 neutrons. But about 1 carbon atom out of every 100 has 1 extra neutron. This has very little effect on the properties of the carbon other than making it slightly heavier. Chemically, it acts just like any other carbon atom. It is called carbon-13. And there's an even rarer type of carbon. It is formed high in the atmosphere when cosmic rays strike atoms of nitrogen, converting them into carbon-14. Carbon-14 is also chemically identical to regular carbon. But the nucleus of carbon-14 is unstable. After some amount of time, which could range from a few days to many thousands of years, carbon-14 decays back into nitrogen. But since carbon-14 is formed at a steady rate, there is a constant level of it in the environment. Out of every trillion carbon atoms in your body, only 1 dozen of them are carbon-14. As long as an organism is alive and eating, it maintains a constant ratio of carbon-14 to regular carbon. But once the organism dies, the amount of carbon-14 in the body begins to decrease. After 5,000 years, about half of the original number of carbon-14 atoms will have decayed. Using this fact, scientists can tell how long ago an organism died.
Big carbon-14 dating. Let's do one more.
Modern physics is dominated by 2 camps. The first upholds Einstein's relativistic model of the universe, an improvement over Newton's immutable mechanics which tick to a universal clock and could accurately predict Hall events. The other supported quantum mechanics, which describes the weirdness at the subatomic level and whose major tenet is that both location and energy of a particle cannot be known without an inherent degree of uncertainty. Relativism and quantum mechanics are reliable and mutually exclusive theories that share a major problem. Both can't be right, and neither describes the overall universe or explains gravity. Enter string theory, a new model for describing fundamental particles and their behavior from the microverse to the macroverse. It could really be a component to the theory of everything. Like the unification of light, electricity, and magnetism, so too should gravity be combined. But grand unification has been possible until string theory, which appears to be able to link not only the gravitational and electromagnetic forces, but also the weak and strong nuclear forces. It states that the fundamental constituents of reality are super small strings of the order of the Planck length, about 10 to the negative 35 meters, which vibrate at specific resonant frequencies. Any particle should be thought of as a tiny vibrating object rather than a zero-dimensional point. Like notes on a cello string, vibration modes produce different particles, electrons, photons, and perhaps gravitons. Strings can split and combine, appearing as particles emitting and absorbing one another, and explaining the standard model of particles. If the theory is right, it carries the promise of more dimensions than the four space-time dimensions with which we are familiar. These tightly curled dimensions are undetectable since they are smaller than the Planck length. There were different versions of the string theory, depending on the type of string and whether or not supersymmetry is incorporated. Despite the specifics, 5 theories emerged, each with the same concept but differing mathematical models. They were different flavors of the same thing and are collectively referred to as M theory. Because there is no known way to probe distances of the Planck length, experimental verification of these strings remains daunting, but exciting new prospects to verify supersymmetry and indirectly detect the curled up dimensions might rewrite the universe.
Ooh. Right, so big idea he's talking about here is called unification. So at this point in this class, there's really these two conflicting laws of physics governing the universe. So anything on a macroscopic scale can fall under the umbrella of general relativity, right? That's the updated version of Newtonian classical mechanics. Okay? So if you say like, why is a planet orbiting a star, or what is exactly its motion going to look like, or can you predict the solar eclipses decades out, or why does a galaxy spiral the way it does, right? That all follows under the umbrella of Einstein general relativity. Okay? And then there's this separate set of laws of physics, this quantum mechanics, which is this packet that we've been working this whole journal. So down at the atomic scale, you have probabilistic existence, Schrodinger's wave equation, you have Heisenberg uncertainty, you have this wave particle duality, right? So it's really weird, right? Now, can you reconcile these two separate laws into maybe one theory of everything? Because there might be some places where these two sets of laws would come into conflict. Can you ever have a large mass in a small space? Because here's your large mass, here's your small space. What laws do you go with, right? What's happening, say, inside a black hole? What's happening in the first second of the Big Bang, right? What's like some general law of physics that could govern everything, right? So one proposal is called string theory. You mentioned string theory there. There are like different variations on string theory. Combine those, call it M theory. Now, one of the difficulties with something like string theory or M theory, it says like down at the order of the Planck length, matters made out of these vibrating waves is how do you conduct a scientific theory to test this? So some falsifiable hypothesis experimentally, right? And right now, things like string theory, they've been around since I think the 1970s about, really just exist on paper in theory. But can you come up with a scientific experiment? That's a little harder. So some call it maybe not technically a field of science, but more of a field of philosophy at that point. Can't come up with a falsifiable experiment. Okay. All right. So that is as far as we've been getting today. Tomorrow we'll do some half-life calculations, and we are getting close to the close of this journal.